Over 2,000 years ago, in his collection of mathematical definitions, theorems, and proofs called the Elements, the Greek mathematician Euclid gave an algorithm for computing the greatest common divisor, or GCD, of two integers. We call this the Euclidean algorithm, and it involves our familiar division process with quotients and remainders. In the 21st century, computer scientist Godfrey Toussaint used a similar algorithm that led to a way to describe what he called Euclidean rhythms in music. We are going to explore both of these ideas in this video. I will use a simple example to describe the Euclidean algorithm, which we will use to find the GCD of the numbers 25 and 95. First, by just looking at the factors of 25 and 95, we can easily identify the GCD. The factors of 25 are 1, 5, and 25, and the factors of 95 are 1, 5, 19, and 95. So the GCD of 25 and 95, which we can denote GCD parentheses 2595, is 5. To start the Euclidean algorithm, we divide 95 by 25. The quotient is 3 and the remainder is 20, and we can write 95 is equal to 3 times 25 plus 20. Next, we divide 25 by 20 and obtain a new remainder, 5, and we can write 25 is equal to 1 times 20 plus 5. And we continue in this way until we get a remainder of 0. For this example, that means dividing 20 by 5 and writing 20 is equal to 4 times 5 plus 0. In the Euclidean algorithm, the last non-zero remainder is the GCD, which we notice is 5 in this case, verifying the GCD that we already found. As we can see, the Euclidean algorithm uses division to find the GCD. When we first learn about division, it is usually through simple examples like, how do we equally distribute 8 slices of pie among 3 people? In this case, each person would get 2 slices, and there would be 2 that remain, since 8 is equal to 2 times 3 plus 2. In a paper written in 2004, Godfrey Toussaint considered a problem posed by Eric Bjorklund, which involved distributing a number of pulses over a certain number of timing slots. The problem can be easily understood by looking at how to equally distribute a number of ones in a binary sequence. Let's say we have a binary sequence that is 8 binary digits, or 8 bits, long, and we want to distribute 4 ones. This means there will be 4 ones and 4 zeros. And it's easy to see that the equal distribution will result in the sequence 1, 0, 1, 0, 1, 0, 1, 0. The question then is, what do we do if there is a remainder? Bjorklund's algorithm works in a similar way to the Euclidean algorithm, and we'll demonstrate it with an example. In this example, we want to distribute 5 ones in a 16-bit sequence. We start by writing the 5 ones first, and the remaining 11 bits as zeros. Next, we fill in a 0 after each 1. When we do this, we can group some of the terms to see that we have 5 tens, essentially, and then 6 remaining zeros. We repeat again by filling in zeros after each 10. And now we have 5 100s and 1 remaining 0. The algorithm stops when we run out of zeros or when there is just one sequence that is different at the end. The simplest way we can finish with our example is to take the remaining 0 and write it after one of the 100s. Bjorklund was able to prove that it does not matter which one, so we will write it simply after the last one. Again, grouping terms, we can easily see this sequence as 100, 100, 100, 100, 1000. What is interesting is Toussaint then noticed this relates to the bossa nova rhythm from Brazil. In musical notation, the ones are written with an X to denote when a percussion instrument would hit, and the zeros are rests. In 16 subdivisions of the beat, the percussion instrument would hit 5 times. One of the more familiar versions of this beat places the 1000 part of the sequence in the middle. We can hear this in the following recording. There are many other examples of the results of this algorithm throughout rhythm. Toussaint coined these terms Euclidean rhythms, and they can be heard in a wide variety of music from all cultures.